Everyone, I am Harshitha and I'm presenting the topic digital to digital conversion. First, let's see what is digital to digital conversion. And digital to digital encoding is nothing but the representation of digital information using a digital signal. So, digital information is the information that we send in the form of bit intervals 0 and 1. Digital signal is nothing but the voltage pulses. So the process in which binary ones and zeros generated by the computer and that are translated into sequence of voltage pulses so that it can propagate through the wire is known as digital to digital conversion. Here binary ones and zeros are nothing but the digital data and the voltage pulses or digital signal, hence the name digital to digital conversion. So here is a figure of digital data which is encoded into digital signal. You can see the digital data 0 and 1 bit patterns, and it is encoded and you will get in the form of the voltage pulses signals, that is digital signals. Line encoding. So line coding is the process of converting digital data into digital signal. So at sender side what happens is digital data are encoded into digital signals, and at receiver side the signal which has been received or decoded into digital data. And line coding schemes are of three kinds: unipolar, polar and bipolar. So we focus on polar and bipolar line coding schemes in this session. Polar encoding is an encoding scheme which uses two voltage levels. One is positive and another one is negative. So by using two voltage level, an average voltage level is reduced, and the DC component problem of unipolar encoding scheme is also alleviated. And polar encoding is further classified into NRZ, RZ, biphase. So NRZ is further classified NRZL and NRZI. Biphase is further classified as Manchester and differential Manchester. NRZ polar encoding. NRZ stands for non-return zero. In NRZ encoding, you can see the signals can be represented either positive or negative, so it never returns to zero. As the name only indicates, it's non-return zero polar encoding scheme. And the most common methods in NRZ is NRZL and NRZI. So let's see what is NRZL and NRZI. NRZL encoding, in this the level of signals depends on type of bit that it represents. If the bit we sent is 0, then the voltage level will be positive, and if the bit we sent 1, then it will be the negative. So therefore we can say that level of the signal is dependent on the state of the bit. Next, NRZI. So NRZI is an inversion of the voltage level that represents 1 bit. So wherever you find the 1 bit in the when you are going through a pattern where you find the next bit is 1, then there is an inversion in the voltage level. So in NRZI encoding scheme, transition occurs between positive and negative voltage that represents 1 bit. And in this scheme, 0 bit represents no change and 1 bit represents a change in the voltage level. Here you can see in this graph that NRZL and NRZI. So the given data, digital data, that is 01001110, and you can see in NRZL as it is polar encoding scheme, we have only two voltage levels, that is positive and negative, and 0 represents positive, so 0 is of positive voltage level and 1 is negative, and 0 positive and 111 negative you can find in that. And in NRZI what happens, you get the transition only when there is a next bit is 1. So you can see here 0, then there is no need of a transition. 1, so the transition occurs. So it changes, it continues to be remain in the negative state, and 0 no transition, 0 no transition, it remains in the same state as it is, and 1, so it is in negative, it goes from negative to positive because of the transition bit 1, and next it is 1, so it goes from positive to negative. Next it is again 1, so from negative to positive, and next is 0, so no transition. So this is NRZL and NRZI polar encoding. Next, RZ polar encoding. So RZ stands for return to 0. As the name only indicates that the voltage pulses should return to 0. So there must be a signal change for each bit to achieve synchronization, and however, to change every bit we need to have three values. So that is positive, negative and zeros, and RZ encoding scheme provides three values. So one is for positive voltage and negative voltage means it is 0 and 0 voltage represents none. So in RZ scheme, halfway through each interval, the signal returns to 0. As name only indicates, it's an return to 0 coding scheme. So the voltage pulses should return to 0, and you can see in the graph that in every bit transition, the voltage pulse will return to 0 before it completes the voltage pulse. In RZ scheme, one bit is represented by positive to 0 and 0 bit is represented by negative to 0. You can see here in the first bit, 0 is represented by negative and it returns to 0 and it goes to positive, and 1 bit is represented by positive to 0 and next goes to negative. Next, biphase polar encoding. So biphase polar encoding is an encoding scheme in which signal changes at the middle of the bit interval but does not return to 0. In biphase encoding, the voltage pulses doesn't return to 0, and biphase encoding is implemented in two different ways, that is Manchester and differential Manchester. Let's see what is Manchester and differential Manchester. First, Manchester. It changes the signal at the middle of the bit interval but does not return to 0. So it changes the bit at the middle of the signal but it does not return to 0 for synchronization, and in negative to positive represents binary 1 and positive to negative transition represents 0 in Manchester, and Manchester has the same level of synchronization as RZ scheme except that it has two levels of amplitude. In Manchester it has two levels of amplitude and in RZ it has three levels. Differential Manchester, it changes the signal at the middle of the bit interval for synchronization, but presence or absence of the transition at the beginning of the interval determines the bit. Transition means binary 0 and no transition means binary 1. In differential Manchester encoding scheme, two signals represent 0 and one signal change represents 1. So here's the graph for the Manchester and differential Manchester, and you can see 0 signal in Manchester. You can see that 0 bit is represented from positive to negative and 1 bit is represented from negative to positive and so on. In differential Manchester, transition occurs only if the next bit is 0, and you can see that as the first bit is 0, the transition from positive to negative it should be, but it will go from negative to positive, and for 1 there is 1, so no transition occurs, it remains the same in the positive, and next 0 from positive to it becomes negative, and next now the signal is in negative level and another next bit is 0, so from negative to it returns positive and so on it occurs. Bipolar encoding. So bipolar encoding scheme represents three voltage levels. One is positive, negative and 0. So in bipolar encoding, 0 level represents binary 0, binary 1 is represented by positive and negative voltages. You can see here 0 bit is already actually represented by 0 voltage and 1 bit is changed. If the 1 bit is in positive and again in next you get the again bit 1, then it will be in the negative voltage pulse. That's what is here. If the first bit is 1 is represented by positive amplitude, then the second 1 bit is represented by negative voltage. Third 1 bit is represented by the positive amplitude and so on. This alteration can also occur even when the 1 bits are not consecutive. If they are consecutive or not consecutive, this transition will occur. Next, bipolar is further classified into AMI, B8, ZS, HD, B3. Let's see one by one. AMI bipolar. So AMI stands for alternate mark inversion, where mark work comes from telegraphy, which means 1. So it can be redefined as alternate 1 inversion. In bipolar AMI encoding scheme, 0 bit is represented by 0 level and 1 bit is represented by alternative positive and negative voltages. As it's bipolar, bipolar is always represented by alternative positive and negative 1 bits. AMI is also one of them. And the advantages of AMI is DC component is 0, sequence of 1 bits are synchronized. What are the disadvantages is encoding scheme does not ensure synchronization of long string of zeros bits. If there is only 0, transition only occurs when there is 1 bit positive or negative. When it is 0, it cannot ensure the synchronization of the long strings. Next, B8ZS. So B8ZS stands for bipolar 8-0 substitution. As the name only it represents, it's a bipolar encoding scheme, and 8-0. This scheme only occurs when there is 8 zeros, consecutive zeros in the bit pattern. In most of the cases, the functionality of B8ZS is similar to bipolar AMI, but only difference is that it provides synchronization when long sequence of zeros bit is occurs. So the scheme is occurred only when there is long sequence bits of 8. It should be 8 times 0 consecutively. Only then the scheme is applied, or else it will be same as the AMI bipolar encoding. B8ZS ensures synchronization of long strings of zeros by providing forced artificial signal called changes called violations. It adds violations when there is 8 consecutive zeros within zero string pattern. When 8-0 occurs, then B8ZS implements some changes in zero string patterns based on the polarity of the previous bit. And the violations, how it occurs, the violations is, it depends on the polarity of the previous one bit, whether the one bit is positive or negative in the previous. Here it is. If the polarity of the previous one bit is positive, 8 zeros will be encoded. As you can see in the figure, if it is positive, it can be present as positive 0 0 0, and you will add a positive, and next negative 0 negative and positive, and the so way it happens in the when the previous bit is 1 is negative, then the 8 bits zeros will be encoded as 0 0 negative positive 0 positive negative. So these are the violations we are adding. And HTP3 bipolar encoding. So HTP3 stands for high density bipolar 3. So this technique is designed to provide synchronization of long sequence of zeros bits. In HTP3 technique, pattern of violation is based on the polarity of the previous bit, as in the previous screen we discussed. In previous bit, what happens, you get the synchronization only when there are 8 consecutive bits, but in this, when there is 4 zeros, 4 consecutive zeros, HTP3 looks at the number of ones bit occurred since the last substitution. And here also same, it occurs depending on the previous substitution of the polarity of the one bit. If number of 1 bits is odd, then violation is made on the 4th consecutive of 0. If the polarity of the previous bit is positive, then the violation is positive. If the polarity of the previous bit is negative, then the violation is negative. So here it is. So if the number of last substitution ones is odd, you can see here, so polarity of previous bit negative is there, so we will change the 4th 0 to negative. If it's positive, we'll change the 4th 0 into positive, and when it is even, we will change the first and the 4th bit. And if the polarity of previous bit is positive and one bit is even, then we will change first and 4th bit to negative. And thank you. Have a nice day.